Again, I misspoke, at least on Monday, if not maybe before. Our last class is not the 25th, it's the 23rd. And our final will be a take home given the week after. So if you have questions, comments, please let me know. So last class, what we did is we wanted to introduce an important topic. So we introduced what's called the normal distribution. Now, we wrote down some scary formulas on class Monday, and I told you not to stress about them because the mathematics that's involved in them is a little beyond what we expect most students in this level of a class to have. So the good news is what you should take from it is that the questions that, we're not asking you to have that level of math sophistication, so do not stress about it. But I do think it's important you understand what equation and what function is going to give us the information we need. So, okay. What should we take from it? Well, so we say the random variable is normally distributed if, well, what? Well, how, what's the proper way to think about this stuff? Or what's, I don't want to say proper because maybe that's a bad way of saying it, but so we'll put it this way. It's normally distributed if its probabilities are given by the following. So we're going to say the probability that the random variable lives between two numbers, which we'll call A and B, if this is equal to, now I don't want to write the scary math thing out, so what I'm going to write out is some English. The area under the curve. And so what do I mean by that? Well, let's draw a quick picture. And if you remember anything from last class, or at least if you have your notes available, from A to B. So, let's draw a picture. So let's say we have so you remember this thing is centered we have this curve, which I'll draw. It's this bell-shaped curve, and it looks like this. We're sketching it a little bit. And it's centered at the mean, and if we take some point, I'll call this point A, and I'll call this point B. And if I look at the area of this curved region, quote unquote, under the curve, if the probabilities are given by the area of this region, then we say it's normally distributed. Does anybody have a question about this? Now, I attempted to give a little motivation of why area is important. And what I did is I told you to think about your simple examples, your coin flips, your dice, and think about the sample spaces, and think about making bar charts or histograms to illustrate probabilities, and think about how those rectangles, the probabilities can be interpreted as areas of those rectangles. And so I know that's not the best explanation, but that at least gives you some intuition why area in some ways should be associated with probabilities. Now, we also had a very specific type of normally distributed random variable, and that is the standard normal distribution. And that is when the mean is a specific number 0 and, excuse me, the standard deviation is 1. So using this definition, and our axioms that we stated many, many lectures ago, we also have, for example, the probability that x is less than or equal to a equals an area, which we'll draw in a second, and the probability that x is greater than or equal to, say, b is going to be equal to some area. So let's just sketch these things quickly. So if I have my center of my curve, which has some, looks like this. And so then if I put some value a, say here, then this is the area that would tell us the probability of the random variable being less than or equal to a. And of course, if I want to know when is it greater than or equal to b, I would have a very similar sort of picture. Now, there's nothing special about the value of a or b. They can be any number. It just so happens that here I've written it as it's less than the mean, but it doesn't have to be. It could be greater than the mean. And so this area gives us the other probability. Okay, does anybody have a comment or a question? And maybe you should have a natural comment or question, and that is, how do I compute these areas? And that's what we're going to get to in a second. Does anybody have a comment or a question? So to quote unquote compute these areas, by hand, what that does is that requires calculus. And we're not in calculus. So instead, we either look them up in a table or use a computer. So for example, if I just Google, I literally Googled normal distribution calculator, and this is the first hit I have. And if I want to compute these probabilities, the computer will do it for me. So for example, if I want to know certain probabilities, I just plug them in. And it's going to spit out an answer for me. So we're going to come back to this in a second, but I just want to illustrate that there's lots and lots of free things that will do this for you. You just have to find them. And if you don't know how to find one, let me know and I'll direct you. No matter what you do, though, whether you want to look them up in a table, which we'll show you how to do, or if you want to look them up or use a calculator, what is common to do, so it's convention. And the reason for this is this allows us to not have 40 tables in the back of a book. So it's convention to convert a normal random variable to a standard one. And we gave you the formula. Z equals X minus mu over sigma. So why is this kind of the convention? Well, let's look at the, if you know the mathematics, what you'll notice is that the standard normal distribution has some very simple and useful symmetries. So first off, if I draw the standard normal guy, which looks like this. So a very cool thing is the following. If I just go, so here we're going to say mu equals 0. If I compute everything bigger than 1, so the probability that z is greater than or equal to 0, this probability is 1/2. And then the probability that z is less than, so this area right here is 1/2. The probability that z is less than or equal to 0 is 1/2. And the total under the whole curve is equal to 1, as we expect, because we know total probability has to be 1. All right, so let's show you how to compute some of these. And by the way, I just did that. If I go back to that web page, notice I want to know, for some reason they call this standard score Z. I don't know. But if I want to know the probability that it's less than 0, I plug in 0 and it gives me 0.5. Okay, so let's compute a few of these. And then we'll show you how to do some applications. What is the probability that Z, and by the way, it's always convention. If we write Z, we mean a standard normal. And if we write X, we will tell you what the mean and the standard deviation need to be. So let's compute the probability that Z is less than or equal to 0.1. So how can we do this? Well, if you have your textbooks, all textbooks of this sort of prob and stats will have in the back, they'll have an appendix with these tables. And so I clearly can't, I'm not going to show you how to do that here because we're not in person, but the internet has these tables as well. So before I do that, let's do this using a standard normal table. Or some people call them Z-scores. I don't know. I don't know why they call them that. I don't like using that. I like saying standard normal table. So what I'm going to do is I'm going to go to the internet and I'm just going to Google standard normal table. And you'll see that what happens is I have these tables. So let's just click on the first one and see what we get. And you'll see at the top, you have to be very careful, the context. You'll see if I highlight this, it says these represent the area to the left of the Z-score. And that's, if you look at my problem, that's exactly what I'm after. So let me go back to this for a second. So the probability that I'm after is I need this area. So I'm going to draw this rather large or maybe not to scale. This is 0.1. What area I need is I need this area over here. This area equals the probability Z is less than or equal to 0.1. Does anybody have a comment or a question or anything? You want to talk about anything? You want to say how this is confusing and you want to stop doing school forever? I don't know. I hope that you don't want to do that. By the way, if you go to YouTube and say how to read a Z table or how to read a standard, you're going to probably see lots of good videos. People are probably very good at explaining it. You guys have all the resources at your fingertips. Okay, so let's go back to that table. I need to, let me show you how to read the table. So if I go back to this table, I need Z to be, here's how we think of this table. So the column here is the first decimal point or the ones digit. You'll see 3.9, 3.8, 3.7, 3.6, 3.5. And you'll see this goes down. So what we need to find is the 0.1 column. And so if I come down here, what I'll notice is this is the column that I'm interested in right here. And then I only asked us to find for 0.1. So all I have to do is go to the right and find the appropriate second decimal place, in which I asked is 0.1. So the answer that I am that I'm looking for is this value right here. So again, I go down the vertical column to find the first decimal space or the ones digit. And then I go across to find the second decimal or the hundredths, as you might remember it is called. So what I get is 53983. So if I go back, this is 0.53983. Does anybody have a question about this?
So is there any like work that you have to show for it?
No, not really here. I mean, I could, depends on how I phrase the question. So I might tell you to draw the corresponding area for a probability. If that's the case, then you should draw something similar to what I drew. But other than that, no. I mean, I could go, so I'll give you an example. If I just went in, if I just said compute this probability, then there's nothing wrong with you going to the internet and saying, okay, let's go to a standard normal calculator. And I come up and let's just say, okay, let's go to a different one. We already had, let's go to this calculator.net. Let's see what this is. All right, so here we go. Here's the z-score. I want to know what? I want to know when it's less than 0.1, right? So I type 0.1 in here. And look how sophisticated this is. First off, it draws the probability I want. Look what the answer it gives me. 0.53983. That's exactly what I have. And it also gives me the associated probabilities. So to answer your question, if all I ask you to do is compute a probability, then you are within your rights to just tell me what it is. That's fine. Does that make sense?
Yeah, I'm good on that now.
Yeah, however, I could say to you, well, I want you to draw a picture that represents the probability. Then you would have to do that. All right, let's do another one. We'll stay on this page. Just so we can go back to that table. What if I said, okay, what is P? How about 0.67? So if I wanted to know that, I can go back to my table. And this time I need to go down to 0.6, which is right here. So I have to come down the the vertical column to 0.6, and then I have to go all the way over to the second decimal, which was 0.7. So where do these guys match? They match right here. So again, the vertical column gives me the first decimal or the tenths, and then the going across horizontally gives me the hundredths. So 0.67, 0.67, and so 74857. And if I go, just for for completeness, if I go back to the internet and I plug that into this calculator, instead of 0.1, I did 0.67, and I hit enter, notice it gives me the same answer. Does anybody have a question or a comment about this? Okay, so that's probably the most basic problem. Now, what if we don't have a standard normal to start with? Well, in this case, we have two options. Option one is find a calculator that does it. Excuse me. So option one is to find a calculator that does a normal random variable. Or step two convert to z and repeat the previous problem. Excuse me. So let's look at an example of sort of this flavor.
Can you go back the slide real quick?
Yeah, sorry.
Thank you.
No, take your time. Sometimes I forget.
All right, I'm good.
Sure?
Yep.
All right. So let's look at.
Please give me a second. Sorry.
No, you're good. Take your time. Let me know when you guys are ready. We good? I'll assume yes.
Yeah.
All right, good. All right, so here's an example that covers this. So assume x is normal with mean, I don't know, let's say mean 28 and standard deviation 5. Let's determine the probability that, say, x is less than 32. Less than or equal to 32. So one way to think about this is, before we do anything, let's to start, let's draw the desired area. So if I draw my normal, so here I have my mu equals 28. And then if I draw my curve, I know my curve is symmetric with respect to this mean. It looks something like this. I'm sketching it. And then we know 32 is bigger than 28. So here's 32. And then the area that we're after is this creature. So this red area is the probability that x is less than or equal to 32. Okay, so what I could do is I could go to a calculator. So let's assume, let's do that on the next page. We'll do this a couple different ways. And again, watching me find a calculator is not going to be the same as you doing it because I have experience with this. So it's probably much more confusing from your perspective. So I would encourage that you learn this by hand first, but I'm of course not going to force you to do that. So the next page here, we'll solve this a couple ways. So solution 1 using a computer. The probability that x is less than or equal to 32. So I'll just go to my calculator. So I'll go back to the calculator. Now, if you look up, you'll see that there's a calculator up here. If you give it the x, mu, and sigma, so our x was 28. Excuse me, our raw score, we wanted to know 32. 32, the mean was 28. And the standard deviation, I believe, was 5. And if I calculate that, it gives me an answer of 0.78814. So if I go back here, I get that this is 0.71844, or if you'd like, 71.8%. Now you'll notice something. If you look at what the computer did, it did the work for us. Notice it actually converted Z. It did it for us. And then it calculated it that way. But let's do it by hand and make sure what we do matches what the computer does. So solution 2 we'll convert to So remember, Z is x minus mu over sigma, which in this particular problem is 32 minus 28 over 5, which is 4/5. Of course, we've been using decimals, so 4 divided by 5 is 0.8. And so what we'd like to find now is we know that the probability x is less than or equal to 32 is the same as the probability that z is less than or equal to 0.8. And so then I have two options now. I use a calculator for this, or I go to the table. And so what I'll do is I'll go to a table, and I'll do that in 30 seconds or so. I think you're caught up. By the way, please interject if you have a question or a comment. All right, so if I go back to my table, I need 0.8. So I come down here to 0.8, and 0.8 is 7814, or excuse me, 78814 right here, which luckily for us is exactly what we got the first time. All right. Does anybody have a comment or a question about that? Okay, so good. So what's the good in knowing all this? I mean, are we just worried about regions, but like what's the application, or where can we use this in the real world? Let's look at sort of a real world problem. So here is sort of a simplified real world problem. So suppose you're a hospital or something, and suppose you need to analyze how many hospital beds you have open at any given time. And then you might be interested in things like what's the longest stay, or what's the average stay. And we collect data, and we'd like to make some sort of, or we'd like to get information from our data. So a local hospital collects data on a regular basis and finds the average, and remember, average is sort of a synonym for mean. It finds the average length of stay after surgery is, let's say, 3.85 days. The data also suggests these times are normally distributed with variance of 2.4 days. So notice I'm being very careful with my words. Just because we collect data, there's nothing that specifically says it has to be distributed normally. We might make assumptions, but that's why I'm using these words suggest. So let's determine the probability a random patient will stay longer than, let's say, 4 days. Does anybody have a question about what the problem's asking? Not about how we're going to answer it, but what the problem's asking. All right. So what we'd like to do is we'd like to use our tools from this class to determine a solution to this problem. So how can we do it?
Do you plug it into the formula that we did where it was?
Right, but we got under what formula are we going to plug it into? You know, you want to try to stick away from saying things like plug things into formulas because, you know, the important part is applying math to the real world and interpreting if your application is valid or not. The mundane thing of finding a z-score, that's, I mean, what we just did in those previous examples, no offense to you guys or anybody else, but there's no skill involved there. I mean, you just saw a computer can do it. So if you can figure out how to convince a person to plug certain numbers in and hit enter, anybody can do that. That's not the skill. Here's the skill. The skill is taking something and formulating it so that you can use a machine to find the answers. That's the skill. So what we need to do is we need to set the problem up properly. So here's what we're going to do. We need to define a random variable. And we need to interpret the English on the previous page in terms of probability. So let x be the length of a stay. What we're asked to do is determine the probability that a patient will stay longer than 4 days. So we need or then I shouldn't say the question, then the desired
So wouldn't it be the probability of x is greater than 4 then?
correct, right. So then the desired probability is p x greater than 4. So there's a few ways you can do this. You can go right to the internet and calculate it, but you have to be careful. What I'd like to do is do it slightly different. I'll compute in the following way. And I'll call this the old school way. So the first thing I'll do is I'll note the probability that x is greater than 4 is the same as 1 minus the probability that x is less than 4 or equal to 4, whatever. And then 2, I'll convert to z-score. And then 3, I'll use a table. So I'm going to go the old-fashioned way. I'm not saying you have to go this way. You can go plug that right into a computer if you wanted. I didn't say you had to solve it any specific way, did I? No, but I'll do it this way just to, and then we'll check our answer on the calculator. All right, so here we go. So here's what I'll do. Note that z is x, which is 34, or not 34, am I losing my mind? 4. Where did I get 34 from? So that's 4 minus mu, which was, I don't remember what I wrote down for that. 3.85 and then 2.4. Notice I put a square root down here because here's a subtlety in the problem. I gave the variance. I did not give the standard deviation. And the variance is the square root. Excuse me, the standard deviation is the square root of the variance. So I don't know why. What is up with 8s? I'm getting 8s. Am I losing my mind? So this should be 2.4. So does anybody have a question about that particular piece? If you have a comment?
I didn't hear what you said about the square root part.
Yeah, so if you look at in the statement of the problem, I gave you the variance. But the standard deviation is the square root of the variance. So that's why I put a square root here. Does that make sense?
Yeah.
All right, so then I'm going to go to a calculator and I will compute these values because, frankly, I don't want to do them by hand. Then again, I don't know that I could compute that by hand. So the z value I get is 0.0968. We'll just round that many digits. All right, so, and then here we go. So I know the probability that x is greater than 4 is 1 minus the probability, excuse me, that x is less than or equal to 4, which is the same as 1 minus the probability that z is less than or equal to 0.0968. And now I'm going to go to my table to figure out this probability. Does anybody have a question about what I've done to this point in the problem? So if I go to my table, I have to go down to 0.09. So here's 0.9. So what I end up getting is 0.53586. 0.53586. And then if I do the arithmetic, I get 0.46414. That's if I didn't make any errors. Anybody have a comment about this question? going once, going twice. All right, now we could go and we could check our answer if we wanted with a calculator, just to check it out. So if I go to the computer and I plug it in, square root of 2.4 is like 1.55. So if I calculate it using a calculator, you'll see I get 0.096 is my z-score. Okay, Ricky, I can't right now, honey. Bear with me 1 second, guys. All right, sorry about that. I got children. Anyhow, the probability that we got was 0.53855, and that matches what we got here for that. And so when you do 1 minus, you get 46414, which is exactly what we got here. So the probability that we're greater than 4 is 0.46145, which is exactly what we got by hand. So if you have a comment or a question about that, please ask, because, you know, as I alluded to, these are the types of problems that you're going to be expected to do. So the sort of the two things that you should think about from today's perspective to this point, like what you should know how to do, is you should know how to understand the connection between probabilities and area, and then you should also know how to compute those probabilities either using a table or a calculator. And then last but not least, and probably the most important thing, which requires knowledge of the first two, is you got to understand how to apply this. I mean, what good is learning something if you can't apply it or you can't use it for something else? So I would encourage you to think about that. And I would encourage you to read the examples in the book and all that fun stuff.
Did you change the 1.55 on the calculator online because it was square rooted?
That's correct. Yep. Yeah, it's a good question. So yeah, I don't know if that was clear or not, but you're right. When I went down here, why did I put 1.55? Because that's the approximate square root of 2.4. Does that make sense?
Yes, sir.
Very good. Very good. Very good. Okay. So again, don't forget, and I alluded to this point in class on Monday. I mean, really, what we're trying to do is we're trying to develop a set of tools that can be used in the real world to analyze and study a variety of problems. We're not suggesting that every piece of data or all data you collect is normal. We are saying that many things in nature happen to be normal or behave at least relatively normal. And so we develop these ideas in hopes that we can use them to answer questions about data if it's this case. Okay. Okay, now what I'd like you to do is I'd like you to take your time machine hat, put it on, and go back to like one of the first days of class. And we talked about these examples. And one of the examples that I kept alluding to is this idea of, let's talk about trying to determine the average height of an adult person on the planet. And one of the things that we realized right away was that it would be impossible to actually measure every single adult human. And one of the things I hope you've realized to this point in the semester, that even though something like that's impossible, that doesn't mean we can't get useful answers. You know, we don't need to flip a coin 1,000 times to imagine that about half the time it's going to turn up heads and the other half it's going to turn up tails. we don't need to roll dice 2 million times to realize that 7 is more likely than 11. So we have certain things that we can get information from, or we can get information from using different reasoning techniques. And one of the things that what we want to do now is we want to say, okay, we realize that many things, population cannot be we can't get data of a whole population. So we want to understand, okay, if we have a whole population, say all the adults on this planet, what information can we get from sampling that population? And then, of course, what connection does that have, if any, to the normal distribution? And so that's where we're headed now. So let's sort of set the stage for where we're going next. So our next goal is to discuss what's called the central limit theorem. And this has sort of played in a role in much of what we've done to this point, particularly when we were running simulations and we were analyzing, what if I do this coin game 1,000,000 times or 100,000 times? So here's an idea. Suppose we have a large population. Whatever large means, we'll put it in quotations. And we take, say, 100 random samples of our population. So maybe each one of these samples has a different number of data points in it, or maybe they're all the same. So one way to think about this is each sample has a mean. So let's give them names. Let's call them X sub 1, X sub 2, all the way up to how many are there? There's 100. So I don't know a better way to list a generic 100 things than to use this sort of notation. So if you think about it, these guys are random variables. That's why I've called them X sub 1, X sub 2, X sub 3. So I have 100 different means. Oh my God, is dinner ready? What are you guys cooking for me over there? Hopefully filet mignon. So we can do the following. We can. So what we can do is we can compute the quote unquote mean of the means, whatever you want to call it. So let's call it like we did before, X bar, and that would be X sub 1 plus X sub 2 plus all the way up. I have 100 of them. And so I would divide each one of those, the sum of that, by 100. So the question we might ask is, how is X bar related to the population mean? Which, if you remember, we've been always called the population mean mu. So does anybody have a question about sort of what I'm alluding to, or maybe not what I'm alluding to, but what I'm suggesting we can do? So let me just reiterate this. We want to know the average height of every human on the planet. It's impossible, excuse me, all adults. It's impossible to measure every adult human on the planet. So what we say is we're going to go take 100 random samples. So I go find 100 people, and each one of those 100 people goes out and it measures 1,000 people. And each one of those 1,000 people has a mean, which we call X of 1, and then the other person has a mean, it's X of 2. So these 100 people do their experiment, we get 100 means. So then we're going to average those out. And what we'd like to know is what, if any, connection does this have with the population mean? And alternatively, or in a similar manner, you might even ask the question, how are the sample variances related to population variance? So these are the kind of questions we want to gain. So if you think about the bigger picture, don't think about the math right now. Just think about the real world issue. If we have any large population we'd like to get information about, what we're wondering is how do we sample so that the information we gain is actually giving us information relative to the actual population? That's where we're headed to. That's the big, in fact, that's almost the big picture in everything when it comes to statistics is how large do our samples need to be relevant? Does anybody have a question about this? Comments? Okay, so we have about a minute left, so we don't want to get too sort of too involved with this, but there is some theoretical tools that give us information about this, and as I alluded to, it's called the central limit theorem. and we will finish that. I don't finish it. That's sort of bad way to say it because we can't really state it in correctness, but we can at least allude to why how it's useful. Okay, it's time to go. Does anybody have any last minute questions? Comments? Things they want to say? All right, well then keep working on the homework. If you have questions, let me know. And I will talk to you guys soon. Be safe. Thank you very much and take care.
Thanks, O'Grady.
Thank you guys. Thank you.